So in this video, we'll take a look at the problem from exam 3 from chapter 10, at least the first problem, where you're asked to determine a moment of inertia about integration. And we have a triangular area, and we're asked to determine the moment of inertia about the x or horizontal axis. So thinking back to that comment that I just made in the last video, this is going to be a much easier problem if for whatever axis you're trying to determine the moment of inertia about, in this case the x-axis, you segment into rectangles which are kind of aligned with that axis. So if we're trying to find moment of inertia about the x-axis, I'm going to segment into horizontal rectangles. And the reason is when I do that, these horizontal rectangles, I know their infinitesimal moment of inertia is just going to be that distance, which is y squared times dA. So that's exactly what I've done here. Actually, this figure is from I didn't write this. Even this writing makes my writing look a little bit bad. But anyways, you're tempted, based upon the content in chapter 9, to break it into vertical rectangles because you have y bound as a function of x. But of course, since this is a linear function, you can do algebra easy and get x as a function of y. And so since we're finding the moment of inertia about the x-axis, break it into horizontal little infinitesimal rectangles, each will have a height of dy and a width of x. So that's the first step for determining dA. And of course, that perpendicular distance is just going to be y squared. So we want to integrate with one variable, dy. So we need to express x as a function of y. You can't substitute this equation directly in. However, you can manipulate it and get x all by itself. And that's what I've done here. X equals b minus b over h times y. Just do distribution and clean up the algebra, and you'll have two power law terms involving y. So all that we need to do, if this is the moment of inertia of each little rectangular chunk, we need to add all those chunks up and integrate over y. We're clearly going to integrate from y equals 0 to y equals h. Sorry, that is a typo, which we can fix now. And we have two terms in the integrand. Just use the linearity, integrate the first, integrate the second, and put them together. And that's how you do problem 10.3 on the actual exam. So not an overly hard problem from a calculus perspective, but hopefully you understand here that what we're doing is actually finding the second moment of this area, which is related to the moment of inertia, which we gave one example in the last video, in case anyone's only watching this video, application if it's important in the cross-sectional design of beams. Namely, if you want to minimize deflection for a given vertical loading, you try to design the moment of inertia to be very large, which namely always results in separating the area from the midline axis of symmetry. So we only have one more topic left to cover in this course. It's the parallel axis theorem and how you compute the moment of inertia of an area that can be decomposed into a kind of combination of multiple simplistic areas.